Okay, so we are going to start our ninth lecture on optimization preliminaries. Again, why are we studying about optimization? As some of you has asked, as Baldin has asked, that the importance of optimization is extremely there in power systems, in every aspect of our life. Wherever you go, you will always find the importance of optimization. These days, if you talk about artificial intelligence, it is almost everywhere. Artificial intelligence is used, even in your mobile, in your laptop, in your air condition, in your refrigerator. Everywhere artificial intelligence is there, and also optimization is also there in every electronic equipment which you are seeing. There is some inside controller which is there, which is running those optimization problems and giving you the solution which you are not aware of. But internally, all these tools, all these appliances, you talk about microwave, you talk about refrigerator, you talk about air conditioner, you talk about your television, you talk about your laptops, you talk about your mobiles. Everywhere optimization is running in the background, and we obviously use them, but we do not know them. So optimization, artificial intelligence, these are always there everywhere. So that's the basic background of it. So as we have already discussed, we in the last class we solved one quick problem, and this gives, I hope you got some good flavor how actually this optimization works. And this is very general formulation I gave, which is a very simple mathematics problem. I did not connect it with any power system problem. This I'll do it after probably one or three lectures. After that, I'll come back to power systems and explain everything in terms of power system. So one thing is very clear. I hope you got this understanding here, that whenever we have an objective function and we have equality constraints, just the equality constraints, no inequality constraints, right? If we have one objective function, if we have set of equality constraints, in this case we can easily solve an optimization problem just by taking the derivatives and equating that derivatives equal to 0. We can solve that optimization problem. There is no issue, right? I hope everyone agrees on this. But as soon as we have inequality equations in this optimization problem, as we saw last time, yes, here I have added one inequality equation. So you observe that as soon as we have an inequality equation in that optimization problem, it starts creating problem in the sense you have some conditional statements, and because of this conditional statements you have to solve all these conditions one by one. And obviously here, when we have just one inequality equation, you have two conditions. Now you can imagine in practical optimization problem, there will be, I can guarantee it will be more than millions. It will definitely, even you just increase the power system size with just a small amount, the number of inequality equations increase exponentially, and this will be huge number of equations, and it becomes really difficult to do these condition type of thing and solving it. So this is a big issue. So in optimization, handling of inequality constraints is always an issue, and today we are going to see how in reality, how actually the optimization problems are solved when inequality equations are there. So this is the method which I told you till now. It's a very crude way of solving it. You can obviously solve it by hand. If you have very few or less number of variables, you can definitely do it by hand. There is no problem. You can use your pen and paper and get an answer. But obviously you can imagine if the number of variables are huge, and if number of equations, inequality equations are huge, then it is really not easy to solve all these problems. So typically, a problem in power systems looks like this: minimization of fx comma u, equality constraints gx comma u, and inequality constraints hx comma u. Here x and u I have separated. U here I am talking about independent control optimization variables, and x I am talking about, they are dependent variables, but they are still a variable, but they are dependent variable. No, now can you guess, in power system context, what are those variable which can be represented as u, which we can call them as an independent or control variable or optimization variables? Can you guess from the power system point of view, uh, what all are those
Active
variables?
power, active power, reactive power.
Good, good,
M
perfect. PG,
and V.
QG are the basically control variables. Yes, and
Frequency and voltage.
uh,
Frequency and voltage.
yeah, frequency does not come in optimization. Why? Because frequency is a issue when there is unbalance in the generation and demand, right? So
Yeah, right.
whenever Pg is equal to P demand plus P loss, so whenever this balance is not there, then only frequency is something else. So whenever this balance is there, then frequency will always remain at 50 hertz or 60 hertz. If you are in USA, it will be 50 or 60 hertz. Whenever this balance is not there, then only frequency will deviate, and the all those issues will start, the all those questions will start, how to bring the frequency back to 50 hertz and everything. So till it is balanced, we do not have to worry about frequency. So that's what in optimization problem, this equality equation is always going to be a power balance equation. So that means we are enforcing that there is no need of frequency, or there is no issue of frequency in the optimization problem, right? So therefore frequency is not an issue. PG, QG, yes, you said it correctly that independent and control variables are PG and QG. What else?
BF and KF.
V, voltage.
Not voltage. Also, there is two power, active power and reactive power.
Yeah,
But I think related to this.
we wrote active power, reactive power here. What else? Means there can be many control variables. Let's say you can control the voltage set point of the generator, you can control the transformer's tap ratio, you can control the transformer phase shifter, you can control that, you can control shunt capacitor, QC or Q inductor shunt, or yeah, QI if I write QC and QI, those are shunt capacitor, shunt inductor. You can always switch it on, switch it off. Those are the control variables. So overall, what I mean to say here, in U, or in when we say in power system that these are independent or control or optimization variables, what do we mean here? These are those variables which can be controlled by an outer environment. So we can easily control these whenever we want to satisfy our objective function, which for example we want to minimize it. So we can always control these in information, and we can set our optimization problem to achieve to its minimum value. Okay, now can you guess what will be set of dependent variables x in power systems? What is there in power system which we cannot directly control, but we want it to be remain within a specified range?
What angle? Voltage.
Exactly. So
Power angle. Load angle.
voltage, especially voltage other than generator buses, so not at the generator. So all the buses where generators are not there, in those voltage, or those buses, voltage angles, this also we want to ensure that this is a dependent variable, because once you set these control variables, then the output of setting of these control values, you get this V and delta, right? Also, can you guess anything else which are other than this v and delta, which are dependent variables? Can you guess that?
Line flows.
Perfect. Line flows, yes. So power flows, PF, QF. These are the not the directly controlled variables. It is independent variable. Once we set these control variables, then we get the value of V delta PF QF. Fine. There can be few more which are indirectly dependent on this PFQF. I can loads are generally comes under control, or rather it is fixed. So either control or fixed, because loads it's an independent entity, right? So for me as a consumer, I never think of switching on or switching off any appliance. So I am an independent variable, right? So it will come under U, but mostly it is treated as a constant in most of the optimization problems. We will see all those things later on. But if you consider loads as a variable, they will come under as an independent variable, right? And G, I already told you that it will be a power balance equations. H could be the inequality equations for all these variables, what you said, all the control variables, or rather I can write for all the control variables, minimum, maximum, for all the X, whatever is the dependent variable, their upper and lower limit, all these will come apart. So yeah, these are going to be our inequality equations, right? And obviously there can be many more depending on your optimization problem, your choice, or your requirement. There could be many other equality and inequality equations. It depends on the choice of the operator who is actually running the optimization problem. They decide what all equality and inequality constraints will be there, right? So this is the way a big optimization problem looks like. And specifically we are talking about power system. So this is the big optimization problem of a power system. Now, as we talked about in previous, if there are only equality equations gxu, then obviously you can solve it comfortably. You just have to take the derivative and equate it equal to 0. You will find a solution. But now, because of this inequality, handling of an optimization problem becomes really difficult, and we will see in this course how to solve that type of optimization problem, or in this lecture today. So I told you before that there are two broad methods: Newton's first order gradient method, Newton's second order gradient method, interior point method, and also we talked about linear programming method. So here we will start with Newton's first order gradient method, and I will tell you the steps how this method solves this problem. And again, we will again be solving a problem, or I'll be giving you this problem as an assignment, and you'll be told to do a hand calculation of Newton's first order gradient method. So let me just start it and explain you how this method works and solves an optimization problem. So the issue always starts with handling of inequality constraints, how this Newton's first order method is going to handle an inequality equation. So the idea is, if an inequality equation which is hx less than equal to 0, if this inequality equation is binding means hx is actually equal to 0, then you do not treat this as an inequality equation, you convert it into equality equations. One way of doing this. And if it is so, Newton's first order method is actually an iterative process, so I'm going to come to that. So here inequality, what we do is if the inequality is becoming equality, or if it is becoming hx greater than 0, even then you fix them hx as equal to 0, right? And for all other hx which are not reaching equal to 0, so then that hx will always remain less than 0. So either this can happen or this can happen, right? So this is one way of doing this handling of inequality constraints. So this type of handling is actually known as hard enforcement. So this is known as hard enforcement of inequality constraints. Why I'm saying hard, because I'm enforcing this h equal to 0. As soon as it crosses or inequality becomes greater than 0, I'm enforcing it to be equal to 0. And what I mean by greater than 0, so let's say for example a generator has a limit of 100 megawatt, and as soon as, let's say, obviously in while solving optimization problem, we get that the PG is going to be 101 megawatt. So what you do, instead of 101, you will force PG to be equal to 100 and then solve the optimization problem again by ignoring this variable PG. Or rest all generators will be a variable, but this variable will be fixed 200, and rest all you will be using as for optimization. And whichever PG is, let's say if PG is 80 megawatt, because the limit was 100, so it is well within the limit, so you will just keep it as less than 0. You will not worry about this in inequality constraints. So that's why we call this as hard enforcement, because I'm forcing the variable to be equal to 0. So this is one way of doing it. So another way of doing it, let me just quickly erase this. So another way of doing this is like this. So what you do, because it's an iterative process, you will see if the voltage, let's say for example, if voltage, let me just talk about voltage. So we generally enforce voltage as in per units, it should remain within plus minus 10%. So 10% means 1.1 and 0.9. And let's assume the voltage is actually going below 0.9. So what we will do, that we will enforce a penalty. This less than is nothing but this is 0.9, and this with a factor of alpha. Alpha is a scaling factor, right? So we will add this penalty in the objective function. I'll show it to you, and we will add this penalty to the objective function, right? So here what I am saying, if let's say voltage which is coming out from the optimization problem is, let's say, 0.7. So what will happen is, let's assume alpha is 1. So this will be 0.7 minus 0.9 is will be 0.2, and square will be 0.04. So it will be a bigger value. And let's say if the error is just 0.89. So it is very close to 0.9, just violated a bit. So it will, the difference is 0.01. So the penalty will be in this case 0.0001, right? So the penalty will be low. So the idea here again same is, instead of forcing what we were seeing in previously, instead of forcing it equal to v equal to 0.9, what we did is we added a penalty, and we gradually, smoothly, we wanted the voltage to come within the limit. We do not want to force it, right? So this is the another way of handling this inequality equation. We'll see how this works in the algorithm. And again, obviously the logic is same. You convert the constrained problem to unconstrained problem. Unconstrained means you form a Lagrange function where fx plus lambda gx is equality equation, and instead of writing mu hx, which is for the inequality equation, we add penalty for those variables which have violated, or those equations which have violated, only for those equations, not for all the equations. Right, so we'll add the penalty for those equations. So obviously if let's say penalty is more, so this is going to be a high value, so eventually the total Lagrange function will be a high value. It will not minimize, right? So obviously to minimize, it will have to reduce this penalty to 0, then only this f, or the total overall L, has to be 0. And as soon as v is equal to vi, then this penalty is eventually go to 0. So this will go to 0. So this will go to 0, that means it will not violate. Right. So again, for this Newton's first order gradient method, because you see we have a penalty, and you can see that if there is some violation, and if violation starts reducing at a faster pace, And so you can imagine the complete Lagrange function, because f is also minimizing, penalty is also minimizing in each iteration. So this problem actually reaches minimum at a very fast pace. If you see in a plot, it reaches minimization at a very fast pace, and that's why we also call it as a steepest descent technique. So it takes this steep and it actually tries to minimize this. So this type of problem, especially if we form it as a minimization problem, we call it as steepest descent technique. So if, let's say, if I tell you in a question that, okay, you have to solve this problem as a steepest descent method or technique, then you have to use this Newton's first order method to solve. So if you do a Google search to find this method, so you can also search for steepest descent technique, you will find the same method. Right? I hope it is clear. Now let us see how to solve this. So idea is same. At the optimum, whatever is the Lagrange function you have made, you will just take the kkt or the derivative in terms of lambda. When you take it derivatives in terms of x, you will have this type of equation where derivative in terms of f, equality and penalty. So you have to take the derivatives in terms of penalty also, because it is there in the Lagrange function as well. And because we have two set of variables, x and u, x is the dependent variable, u is the control variable, so you have to take the derivative in terms of u as well, and this will be the derivative equation. Now let us see how we solve this problem. Right, so the first step is you have to take an initial guess for u. You have to make an initial guess for u. U means control variables, right? Control or independent variables. You have to take an initial guess for that. With that guess, just put this u into this first equation, because this equation only involves or only is a function of x and u. So if you have assumed all the values of u, then you can just put the value of u in the first equation and you can get the value of x. Fine. Because this equation is equal to 0, you can do the mathematical jugglery and then you can find the value of x. Now, once you have the value of x, you just put that value of x into this equation, second equation. So in the second equation is a function of x, u and lambda. These three variables are there in the second equation. So you have initially assumed u. You got x from the first equation. This is assumption, and this is from the first equation, and you can put all those values and you can find the value of lambda. Yes, can we do this? Now what you have to do, you can easily check from this third equation that you have to put the values of x, because the third equation is dependent on u, x and lambda, and you have got all those values. So you have to put all these values x, u and lambda, and you will not actually equate it to equal to 0. You will actually find the value of that, and we want that value to be equal to 0, right? In the third equation you can see that this has to be equal to 0, but obviously because we have assumed the value of u, it might not be exactly equal to 0. So what we do, instead of taking it equal to 0, we will calculate the value of partial derivative of L with respect to u, and then what we'll do, we'll update the u, whatever initial u you have assumed, we will minus b, and whatever is the partial derivative of L with respect to u, this value is coming out to be. You will take the difference and update the u, and again go to the second step, because you now have a new u value, and you will put it in the first equation, again find the value of x, and then again put the value on the second equation, get the value of lambda, and then again put all those x, u and lambda in the third equation, find the partial derivative of L with respect to u and find the value. If it is equal to 0, you can stop. If not, then so I missed out on that, del u, if it is equal to 0, then terminate, right? If not, then you keep on iterating and keep on updating this value, right? I hope it is simple. I hope you got the idea. Now in this, one thing is very important, that this penalty is only added in the, you might have to take the derivative at every iterative step, because penalty is only added when x or u are violating. Otherwise you will not add the penalty, right? Only when it is violating, then only you will add a penalty. If it is not violating, why will you add a penalty, right? So just make a note of it. Means, for example, let's say we talked about voltage has to be zero point 0.9 and 1.1. So if let's say voltage is 0.8, then you definitely add the penalty. But if let's say voltage is, let's say, 0.95, then you do not add a penalty, because this is already within limit, so you do not need to add a penalty. I'll give you an example to solve, and you'll get a flavor of it. I hope it is clear, Newton's first order gradient technique. Right. So just quickly, I'll wind up with some comments about the method. So the method is basically this partial derivative of dl by du is actually a gradient vector. It actually gives you a direction in that. So when I said it's a steepest descent, so this direction is actually coming from this gradient vector, and this always moves in the negative direction. So because negative, because we are updating u new is equal to u old minus beta by u, and because of this minus, we always move in the negative direction, because we then only will arrive at the minimum solution. Another thing is that dgu by partial derivative of g with respect to u and partial derivative of g with respect to x are kind of a Jacobian matrix. I hope you remember this name from the power flow expressions. So this is a equivalent of Jacobian expressions. And just few in terms of handling of inequality constraints, I mentioned there are two methods. One, you can enforce it in a hard penalty. If you enforce a hard penalty, then you do not need to add the penalty part, what I mentioned. And if you do not enforce a hard penalty, then you have to add a penalty factor based on that quadratic function. So both has advantages and disadvantages. If advantage for this is that you are enforcing an exact enforcement, and because of exact enforcement, at times in some problems it might help you in fast convergence. When you are implementing in a soft approach means based on that quadratic function factor. Here it is gradually forcing the optimization problem to, or that variable to bring within the limit. So it is gradually doing it during the iterative process. So probably what will happen is number of iterations will increase. Now both has a disadvantages. Can anybody guess here which all are the disadvantages? Advantages I told, disadvantages, can you guess?
Instability problem.
Sorry?
Instability problem.
Instability in which one? The first one or the penalty approach one?
The first one. The first one.
First one, I know first one will not have an instability. It will have a slow convergence, and optimality will not be there. So yeah, exactly stating this stability. No, stability will be an issue here in penalty approach, but not in this inequality to this exact enforcement method. Why? Because we are forcing it. So what will happen, that two things can happen. One is that there can be a premature convergence, means the problem can converge much faster, and because of that premature convergence, your problem may not arrive at actual optimal solution. It might arrive at a local optimal solution. that could be an issue. Now here in penalty approach, what you mentioned that regarding this stability, here it can happen. Let's assume if problem is almost approaching an optimality solution or optimal solution, and let's assume a variable during that time, a variable goes to goes towards uh, goes beyond its limits, or goes towards violation limits. So what will happen, you will add a penalty there, and because we know that the problem is reaching towards an optimal solution, but because we are adding that penalty, immediately the problem may move from that optimal solution to some other solution. So you might face a issue of an oscillatory convergence, and if this oscillation is huge, obviously yes, instability can happen, right? So this is one thing, but let me just quickly tell you about the disadvantages. In this exact enforcement method, the matrix size increases because obviously number of equality equations are more, so the matrix size what you see here will increase, or the problem size is increase because you have more number of derivatives. You have because we do not take the derivatives corresponding to inequality equation, we take the derivatives in terms of equality equation. So the more because we are converting into equality, so the equality equations number will increase, and therefore the problem size will increase. Whereas if I come to the penalty approach method, obviously in here, as I told you before, that oscillation can happen, and because of which inexact binding can happen. Inexact binding means probably the voltage will not arrive at 0.9, but it might remain at 89, 0.89 or 0.899. So there might be some inexact binding inequality which remains. Also, choice of alpha, the scaling factor, also the beta, alpha and beta both is very difficult, and it because we are doing it heuristically, and we are choosing that value randomly, so the choices may not be proper, so that is also a very difficult task. So broadly, if I say there are two, there broadly in this Newton's first order method, the advantage is that it is built upon the original available model, which is actually the equality equation. We know that if we take the derivative of those equality equations, we'll get the solution, but in this method they are just adding some algorithm to compensate or to include the effects of inequality equations. Again, coming back to the disadvantages, that this here handling of inequality, although they are able to handle it, but still at times not at times, often it is not able to handle inequality equations. Also, as I told you before, choice of alpha and beta are very difficult, and the convergence is extremely poor in both the cases. Either it is premature convergence, or if it is converging, probably it might not be able to handle inequality equations properly. Broadly, we say that this first order gradient method are least popular. People generally do not use it. They are mostly not used in practical usage. But if I'm going to explain you, okay, oh sorry, I have completed my time. So in the next lecture, I will tell you about the Newton's second order method, and there you will see that is actually one of the most popular method. So there